Jason, so PQC, we have some algorithms. We have some FIP standards. These keys are a lot bigger than we had before. Surely they're big enough, right?
I wish I could tell you with certainty, but people who truly understand this stuff, I'm just reporting from the field. Okay,
Right.
I'm reporting
this
what
gets super mathy. Yes, go on.
this gets crazy. So here's the debate, Tim.
Okay.
I'll translate this into English that all the listeners of this podcast understand. Are the keys big enough?
Okay. The worry being that because if the keys aren't big enough, there's just not enough entropy, and it's just not gonna. It's gonna be too easy to factor.
It comes down to this theoretical issue, Tim.
Yeah.
Let's say you could solve an everyday problem, but the worst case of that problem is we assume you couldn't solve it because it's the worst case. But if you can solve the everyday problem version of that problem, then it's very safe to assume that you're not that far from solving the worst case. And so here's what I mean.
Okay.
Do you remember when I gave you the way gigantically oversimplified shortest vector problem of lattice mathematics explanation? Remember that I talked to you about those poles in multiple football fields, and you start twisting the football fields?
Yeah.
Okay. So that explanation, part of the reason I say it was extremely oversimplified is because I'm talking about the worst case scenario in the universe. It turns out that the private key, if you go with that worst case problem, the keys are just too big. And so there are compromises made. So the assumption is that no quantum computer could ever break the mega problem. But when you look at the keys, you're going, oh my God, that we can't possibly pass that through the NIST process. They'll never accept a key that's that big. It's not pragmatic. So what they then say is, okay, we'll make it difficult enough. Okay, let's figure out what the average case is, right? The practical reality of what is, the problem is, Tim, when you're making these assumptions between full academic theory of the problem, and then you start to try to make smaller versions of that in order to reduce the key size. I think I came up with an analogy. Let's say that you had a bulletproof vest, and it could stop a 45.
Yep.
And you're proud, man. You're like, I can walk around, I can get shot with a 45. I mean, it's a terrible analogy, but we're talking about security here.
Sure.
All right. What happens if your adversary actually has like a 50 caliber? And you're like, I've seen this take a round.
Right.
Well, did it take a 50 caliber?
Right. Yeah.
And the worry is that the adversary, if they can solve any of the problem, which is very possible, like an average type of problem, they might have eventually or might actually have enough to break the full complex problem, which means we do have to make more critical decisions about what the correct key length is. We were talking about novelty in PQC algorithms.
Yeah.
We know what the bit lengths and RSA and ECC do for us.
Right.
I don't think we fully understand what adversary will do with various key lengths in PQC, Tim.
Sure. So what happens if we determine in the future that they're not long enough?
Then I think the problem, Tim, is there's going to be a bit of an oops moment, perhaps, where we start building systems that are capable of handling a certain key size, and we don't leave much headroom.
Right.
What happens if all of a sudden NIST says, oops, the math is fine. The math is fine, but you got to make it more complicated.
Yeah.
Like more bit length.
And so, so for instance, let's talk about photosynthesis. Photosynthesis is this clever restructuring of the key exchange process that fits the material that needs to be exchanged into the available timeout footprint. But barely. And it's almost like this astounding coincidence that if you restructure how it works, you can get all the pieces in, right? And if you make those pieces bigger, photosynthesis as a strategy might not work.
Well, Tim, I think what you really have to think about is the unraveling of a Merkle tree.
Mm-hmm.
If the key length chosen for the DSA, the signature on the tree. So in other words, if you're using ML-DSA, a module lattice signature algorithm, then that may be perfect math. The problem is that choosing your key lengths, what happens if we got it wrong? And the history. So imagine, Tim, I'll end the podcast with this.
Okay.
Wouldn't it be crazy
if
you were using ML-DSA with X key length on day one with Merkle trees?
Okay.
And you had a whole pile of certs that got hash, issued based on that. Think about the harvest now decrypt problem. When that's public.
Yeah.
And it turns out that key length is now too short and the bad guy can unravel it.
Okay, right. So you could defend against a man-in-the-middle attack sometime in the future by implementing bigger keys. But you could not defend against a harvest and decrypt, not only conducted against a traditional algorithm, but against a PQC algorithm with keys that are too short.
Okay, correct. So therefore, I'm going to push this one step. We could have another podcast just on the next thing I'm about to say.
Okay.
What does that mean about lengths of certificate lifecycle when you're not even sure of bit lengths? It means 5-year certs don't make any sense.
Yeah.
For private, right? Private use cases.
Yeah. I mean, right. The thing about shortening certificate lifetime from a crypto agility perspective, because there's multiple benefits to it, but from a crypto agility perspective, the shorter the certificates get, the less benefit there is in continuing to shorten them, right?
Right.
Okay, so instead of having things hanging around for 3 months, I have them hanging around for 1 month. How excited are they about that, really, right? But yeah, when you get into these long-lived things, these 5-year things, that's a crypto agility problem.
If it turns out that ML-DSA dash something is all of a sudden deprecated, how fast do you want the certificates that were issued off that tree to be dead?
We know we'll all just replace them. Nobody leaves those things sitting around forever. You know that, Jay.
Sleep well at night, Tim.
All right. Bye.
Thank you.